Today we want to continue thinking about antiderivatives and finding antiderivatives. We have the Riemann sum, which is our discrete sum. When n goes to infinity, the number of rectangles goes to infinity, we end up with our definite integral, which is our continuous sum. It's a weird thing to say. And we have the fundamental theorem of calculus offering antiderivatives as a way to calculate definite integrals. The difficulty that we run into is, even though integration and differentiation are almost inverse operations, where differentiation is nice and straightforward and summarized with the three rules, integration is messier. We have to have a lot more tools at our disposal and be a lot more flexible with how we look at functions to deal with finding antiderivatives. We don't even have to go that far for seeing a variety of techniques. Here we have three very similar integrals. The integral of 1 over x squared plus 1, the integral of x over x squared plus 1, and the integral of x squared over x squared plus 1. The first one is just a memory check. The integral of 1 over x squared plus 1, this is just a memory check. We just have to remember that the derivative of arctangent is 1 over 1 plus x squared. So when we invert that process, the integral of 1 over x squared plus 1 is arctangent of x plus c. We got to remember this is not, these are not exactly inverse operations of each other because of that plus c. But very close. Only difference is the plus c. So the integral of 1 over x squared plus 1 is arctangent x. The second example, which we'll hopefully look at today, is x over x squared plus 1. For this, we're going to use, we don't recognize this one right away, but we're going to have to learn a technique that we could use to apply to this second integral. So we're going to use integration by substitution. So this second one will require the technique of integration by substitution, which is the anti-chain rule. Integration by substitution is our anti-chain rule. Our third integral here is x squared over x squared plus 1. And this is, nope, not substitution at all. Even though all we've done is increase the degree in the numerator by 1, we've got to do something else. Fortunately for our heroes, that something else is just a little bit of algebra. Unfortunately for our heroes, that something else is just a little bit of algebra. So when we look at this rational function, we see that the degree of the numerator is equal to or greater than that of the denominator. In this case, equal. So that's how we look at a rational function and say improper fraction. So the degree of the numerator is greater than or equal to the degree of the denominator. So this rational function, this is how we read a rational function and relate it to an improper fraction. If the degree of the numerator is greater than or equal to the degree of the denominator, this is the improper fraction of rational expression. We deal with it the same way that we deal with an improper fraction with numbers. We take our improper fraction, we perform long division and come up with a mixed number. We take an improper fraction. We perform the operation of long division. And we land on a mixed number. Just as a reminder, an improper fraction would be a fraction like 5/3, where the numerator is greater than or equal to the denominator. We do long division, 3 goes into 5 one time with 2 left over, and then we write it as a mixed number 1 and then 2/3. Like we were pointing out yesterday, it's important to recognize that when we write 1 and 2/3, that means 1 plus 2/3. Makes sense. Plus means and means plus. Once we recognize this is 1 plus 2/3, then if we mess the process up, we're okay with seeing things like 2 and negative 1/3, which is the same as 1 and 2/3. So what we have is this improper fraction of x squared over x squared plus 1. We're going to do long division to convert that into a mixed number format. So we've got x squared over x squared plus 1. We're going to do long division. One of the weird things that we don't do when we're writing polynomials is to write our 0 terms. We have to do that with numbers because we use place value to indicate powers of 10. With polynomials, since we have to write the x factors in our terms, we don't write the 0 terms. So instead of saying x squared plus 0x plus 0, we just write x squared. But if we wanted to write 100, we can't just write 1, because we've got to let people know that 1 is occupying the 100 spot, the 10 squared. So we say 1, then 0, then 0. So we're kind of doing the same thing here, plus 0x plus 0. Now we've got to think, how many times does x squared go into x squared? And the answer is obviously 1. But that's not a very good way of asking the question, because what the heck does that mean anyway? Right? We have to think. One of the reasons that the way I was taught was take x squared and divide it by the x squared. I'm like, well, dude, how does that relate to the process that we had before? Right? Because I can't say 5 divided by 3, because that's what we're trying to figure out. And if we knew that, we wouldn't be writing this down. But if we think about it differently, how many times can we subtract 3 from 5 without going negative? That's what we're doing in this process. That's what we're asking when we say, how many times does 3 go into 5? How many times can we subtract 3 from 5 without going negative before we hit 0? How many times can we subtract x squared from x squared before we hit 0? And it's 1 time. Some people would say you have to put the 1 in the proper place. So let's just follow that plan. So I'm going to put all my constants over here. 1 times x squared is x squared. 1 times 1 is 1. And then we'll subtract. Remember, the point of this process was to ask, how many times can we subtract x squared plus 1, or x squared from x squared without going negative? The answer was 1. So now we're going to do that subtraction. X squared minus x squared cancels out. 0x minus 0x is 0x. 0 minus 1 is negative 1. Now I need to make fractions if I want to subtract x squared from -1, so this means we stop. Here's our remainder. And so our mixed number form for this expression, the whole number part is 1, and the fraction part is -1 over x squared plus 1. No trick to it, it's just a simple trick. And you learn it in like 4th grade. You have to apply it, polynomial. So instead of integrating x squared over x squared plus 1, our technique is to identify this as an improper fraction, use our long division technique to write it as a mixed number, and then integrate the result. Because look at the terms that we have or look at the terms we want to integrate now. I've got this 1, that's easy to integrate. Add 1 to the exponent, divide by the new exponent. The other term is -1 over x squared plus 1. That's just a memory check. The integral of 1 is x. The integral of 1 over x squared plus 1 is arctangent x plus c. No fancy, no fancy calculus technique. We rewrote the problem using algebra. This is an important thing to recognize. You're stuck with what to do. You're looking at this algebraic expression. You're stuck with what to do. Do some algebra on it. When you have a problem with trig functions, look at all these trig functions running around. Start looking for trig identities that will allow you to manipulate your expression. 3 tricks of mathematics: multiply by 1, add 0, change your variables, move some things around. How's everybody okay? This gets us to a larger point when dealing with rational expressions. So taking a look at these 3 rational expressions, I've got 1 over x squared plus 1, x over x squared plus 1, and then x squared over x squared plus 1, which is standing for everything else. If the degree of the numerator is greater than or equal to the degree of the denominator, that falls in the category of the improper fraction, in which case we do long division. We only need to worry about 1 over x squared plus 1 and x over x squared plus 1. Every other rational expression with an x squared plus 1 in the denominator, we're going to do long division, break off a polynomial, and then we'll have a fraction that's either 1 over x squared plus 1 or x over x squared plus 1. It has to be this way because of this comparison that we want to make. If you do this process with an improper fraction and do long division, you'll get a whole number and a proper fraction. Proper fraction. Any questions? So it's always going to be, you'll have our improper fraction, we'll do long division, and we'll end up with a mixed number. In terms of polynomials, or sorry, in terms of rational expressions, the mixed number will have a polynomial plus some proper fraction. In which the degree of the numerator is strictly less than the degree of the denominator. So for a denominator of x squared plus 1, there's either constant over x squared plus 1, memory check, x over x squared plus 1, substitution, which we have to learn. Everything else. There's everything else. Any questions? How's everybody okay? This is a weird place to start talking about finding antiderivatives. You were in my Calc 1 class, you know that I'm much more organized about how we start finding antiderivatives. Since we're finding more antiderivatives this semester, we need to remember that we might need to improvise at some point. We have to be ready to look beyond just whatever technique we have. That make sense? We've got to think about algebra. We're going to have to think about trigonometry. We're going to have to remember all of our tricks to deal with this problem so that we can get through this class and, oh yeah, and then never have to deal with this problem again until like your siblings are in calculus, which you don't really have to worry about because you know you can't tutor your siblings. You'll just end up in a fight. If you have successfully tutored a younger sibling in math, then I don't know. I guess you have like a healthy relationship with your siblings. For the most part, you just end up in a fight. Or in the future, you're going to have children that are in calculus. I promise you, you will not know what the F is going on when they're learning calculus. Because things will have changed and it'll just make you mad. It'll poke you right in the ego. And at that point, it's really important that you just say, sorry, kid, I can't help you. I knew this once, but I don't anymore. Let me get you some hot chocolate so you can feel better about things. But you're going to have to sit with this discomfort. Do you know what I mean? This is super critical that you don't let your ego get in the way. You haven't done math in decades. Why do you think you're still going to have those skills? Decades ago, I was a pretty good swimmer. Now, I'm not even sure I would float. I'm not even sure I know how to do it anymore. You know what I mean? It's really annoying. Because then parents who let their ego get in the way, thinking that they should be able to do their kids' homework, get mad at the teachers. And then they tell their kid, your teacher is wrong. I know what I'm talking about. Based on my years of experience not teaching, the fuck? Get the fuck out of here. All right. So there are other things going on. Just looking ahead, I want to plant this right now. When dealing with rational functions, we only care about denominators when they're linear or quadratic with complex zeros. Any bigger ones, we don't care about. Denominators are cubic, algebra. Denominators are fourth degree, algebra. The only ones that we have to know about are linear and quadratic with complex zeros. Once we learn the technique for this x squared plus 1, that's standing in for our quadratic with complex zeros. That takes care of everything. Algebra takes care of the rest. And when we have a quadratic with complex zeros, we have to know if the numerator is constant, that's the memory check, or linear. Once we have those, we're done. These are the only cases that we need. So let's take care of that middle case. What if we have a linear over a quadratic with complex zeros? Our first technique is going to be integration by substitution. This is the anti-chain rule. Integration by substitution is the anti-chain rule. So let's remind ourselves of how the chain rule works. Remember that the chain rule is for finding derivatives of compositions of functions. This is the first rule that we learned about differentiation, because this is the one that's always in effect. It's just that sometimes the derivative of the inside was 1, so we didn't really have to worry about it. But the chain rule is always in effect. The chain rule says take the derivative of the outside with respect to the inside. And then multiply by the derivative of the inside. df dg times dg dx. Take the derivative of the outside with respect to the inside, then multiply by the derivative of the inside. I'm not sure what incantation you use to invoke the chain rule. That's the one I say. Actually, I was raised to say, take the derivative of the outside, leaving the inside alone, then multiply by the derivative of the inside. One thing that makes teaching math so difficult is what we were taught all these faulty incantations. But it's the one that our teachers, that worked with our teacher. And now they don't even think about it anymore. Take the derivative of f with respect to g, multiply by the derivative of g with respect to x. Chain rule. Let's look at an example. So if I want the derivative with respect to x of cosine of x squared plus 7x minus 3 I've got a composition of functions. My inside function is the polynomial, my outside function is cosine. So we take the derivative of the outside with respect to the inside. Take the derivative of the outside, the derivative of a cosine of a thing is minus sine of that thing. And then multiply by the derivative of the inside times the derivative of that thing. Everybody sitting out there saying, yes, yes, we remember the chain rule. We're good at chain rule. Wait a second, is there going to be a quiz on chain rule? No? Yes, we remember chain rule and we are very proficient in its use. Remember the first rule of learning antiderivatives. All the derivatives that you know are now antiderivatives that you know. So if instead of differentiating cosine of x squared plus 7x minus 3, if I ask you to integrate negative sine of x squared plus 7x minus 3 times 2x plus 7 dx, we know that this is going to send us right back to where we started, plus c. So it's going to give us a cosine of x squared plus 7x minus 3 plus c is the only part that we have to change. Just go the other direction. That's the anti part of antiderivative. To turn this into a technique, we need to see if substitution is going to work. Here's how we use substitution. Let's talk about the technique of substitution. The substitution that we're going to make is the inside. We're going to say, let's let W equal the inside. This is the substitution that we want to make. Find the derivative of your inside. And then rearrange. What we need to answer here, we're not just following some program. We are trying to make sure that our technique is going to work. We want to start with making W equal the inside. We have to know if that's going to work. Once we make the substitution, we have to think, what's my dW? Here's us figuring out what's my dW. Once we decide on an inside function, we immediately have to decide what dw do we need to make this substitution work. Then we make our substitution. So I see this g prime of x dx, all this is going to be replaced with dw. G of x will be replaced with w, so our integral becomes the integral of f prime of w dw. The important thing to happen here is that there are no more x in our integral. No more x in the integral means the substitution is working. Now we've got a nice simple integral. What's the antiderivative of f prime of w? We can integrate. The integral of f prime of w is f of w plus c. And then we resubstitute our w back in. We translate the problem back to x. Four steps. Start with your integral in w, or sorry, your integral in x. Do a substitution to get an integral in w. Integrate that, and then translate back to x. Three great tricks in mathematics. Add 0, multiply by 1, change your variable. How's everybody okay? It's hard to tell because it's an 8 o'clock class. And you all might be experienced enough students to know how to sleep with your faces open. Some of you can sleep and even move around. Maybe it looks like you're taking notes. You're like sleeping with your hands like, and you even blink. That's an important college skill. Oh, you should know it's kind of less important in this class because if you really need to sleep, you should just stay home, turn Zoom on, and then go back to bed. Or just log in and watch it on YouTube later. Then you can watch it at double speed and it's not as boring. And when I'm doing something like this, where it's like punctuating, no math is going on. You see like the screen freeze. Just fast forward like 10 seconds. So not only are you moving at double time, you're like skipping over the commercials. I should just record all this and stop showing up myself. I'm waiting for a hologram to show up. I want hologram teachers because that would even be better. Then I wouldn't have to look like me It could be like 100 years from now, they could just keep using old lectures and then they just keep updating my appearance. That's the key. Because I can't get Dwayne "The Rock" Johnson to come in and guest lecture. He doesn't return my calls anymore. Stupid restraining order. But if I could have hologram Professor Leach teach class, then I could just alter the appearance. And furthermore, I could just do that. You could do that individually. So like you're playing along at home, it's like, well, I don't want to watch Professor Leach, like regular Professor Leach teach math. I want to watch Dwayne "The Rock" Johnson teach. So you like, there's a microtransaction, you pay 99 cents, get the special edition Dwayne "The Rock" Johnson skin for Professor Leach, and then he's doing it. You know what I mean? And then they'll have all kinds of special editions. Oh man, I'm gonna get the whole "The Rock" pack. So it could be like one day it could be like the Scorpion King. They go, oh no, that's the worst one. Then you could have, then if you really want to flex on people, so like if they start teaching this class at like Harvard or some shit and you have to show off to your friends, then you could have special one of a kind NFTs. Be so much better than spending money on textbooks when all the information in the textbook is available for free on the internet. There's nothing that I'm going to talk about in this class that you can't just find out for free by asking the internet. I think I'm going to go and ask ChatGPT to write me a new calculus textbook. Then release that as open source and destroy the calculus textbook industry. I'm just kidding. They've already pivoted by putting the problems online. That's what their product is. They finally caught up. It's like, oh, we can't just like print books with the same shit in them. You know what I mean? I wrote Jurassic Park. Didn't Michael Crichton write that book? So yeah, I just kind of copied it and just released it again and called it Jurassic Park, 2nd edition by new author. That's what calculus books look like, by the way. What's the title of this calculus book? Calculus. What's the title of the calculus book that I learned calculus from? Calculus. It was a completely different book. They just called it the same thing. Well, come on, man. Show a little creativity. Let's see substitution applied to this problem. We have to make W the inside. So the thinking is, I want to make this substitution because it looks like this is the inside function. Then we have to verify that this substitution is going to work in this problem. And so I need to find the dw. What's my dw? If w is x squared plus 7x minus 3, then dw is 2x plus 7 dx. And I look back and I say, have I got that? And the answer is yes. This is my w, here is my dw. This substitution will work. Moreover, I can see the function that I'm actually going to be integrating. I'm going to be integrating a minus sign of w. We make the substitution, then the thinking is, what do I need to make this substitution work? Do I have that? For example, if I change that 2x plus 7 to a 2x plus 5, all of a sudden, this is not a substitution problem. I don't have the dw that I need. I want dw to be x squared plus 7x plus minus 3. To make that go, I need a dw of 2x plus 7 dx. And we don't have that. I've got a 2x plus 5. That's not good enough. This is why we don't want to go on autopilot and just assume that a problem in the substitution section is just automatically a substitution problem. You don't get to know substitution by just knowing substitution. You have to know what's not substitution. You have to know when stuff isn't working. Any questions? This is a check engine light. You can't just ignore it. Okay, it'll be fine. Maybe the check engine light is on because you just didn't tighten the gas cap down. Maybe the check engine light is on because you're about to throw a bearing. I don't know. And you don't know. Make sure your shit gonna work before you just assume that it's gonna work. That's it for today. I will see y'all on tomorrow. Everybody have a good day and thanks for playing.